Okay, differential equations. We've got day 2 of section 3.1, Newton's law of cooling and heating. This will be a separable differential equation. And, our learning target, you can see at the top, I can solve Newton's law of cooling or heating problems. I think it's super important for you to be aware that just as you could, say, take a hot cup of coffee or tea and let it cool to room temperature, we just as well could take an item out of the freezer. Maybe take something that was frozen, a frozen box of vegetables, for example. If we brought it out into this room, over time it would warm up, it would heat up. It would heat up to the same equation in general terms. That might be surprising. We're going to see that right now. What we see is we've got a differential equation. D capital T. T is your temperature at time little t. So little t is a given time. So we're interested how our temperature changes with respect to time. It will be proportional to the difference of the temperature of the item at a given time, at that moment t, and also T sub m, which is the temperature of the surrounding medium. It's a constant, and this surrounding medium a lot of times we'll just refer to as room temperature. And K, of course, is a constant. But let's very quickly derive what's happening right here. One moment. Okay, what's cool about the general setup here is it is in fact separable. So let's get all of our capital T's together. And by the way, I'm going to divide both sides by T minus T sub m. And then likewise, I'm going to then multiply both sides by little dt. So I've got my constant right here. And please understand, I don't know at this point whether we have a heating or a cooling problem. We are in no way told that the temperature of the item will always be hotter, or higher, I should say, than the room temperature. This could be a Newton's heating problem, like we took a frozen pack of vegetables out into this room, in which case at that moment our temperature would be less than room temperature. So, wow, that complicates things, but that's fine. We can definitely proceed. We're going to integrate. And on the right side, of course, we'll have K little t plus some arbitrary constant. On the left side, we're going to have the ln. Do I need absolute value here? Yes. Guys, I don't know whether T minus T sub m is positive or negative. It could go either way, depending on whether it's a heating or a cooling problem. But rest assured, right now, we can exponentiate. We can go e to both sides, and that would leave us with T minus T sub m. And as we're working this thing out, you could very quickly remember this very famous property of algebra that x to the a times x to the b is equal to x to the a plus b. This time we're just going to work from the right side to the left side. So what I'm really getting at is this would be e to the kt times e to the c. And of course, right now that e to the c is a constant. It's just some arbitrary constant, so I could even call it C1 to maybe distinguish it and move it out in front. But I'd like to get rid of the absolute value. And as I do that, I'll get T minus T sub m would be plus or minus C sub 1 e to the kt. But thank goodness, a positive or a negative will simply be absorbed into that constant. So you could even call that C2 if you'd like. Now, by the way, you very well could be wondering about this as we wrestle through here, what's really happening. But suffice it to say, it looks like we've got a K up there, we've got a C sub 2. It's enough, guys, to just add your T sub M. And this, by the way, is in fact your general formula for Newton's law of heating or cooling. It's really neat that you're always using this formula here for either case. And we're almost done with the lesson, thank goodness. If we're just using this general formula, just like we were using exponential growth and decay, let's go ahead and deal with one problem right now and try to work this out, knowing that right off the cuff, if we're working with the Newton's law of heating or cooling problem, ultimately, guys, we're working with this formula right here. We're not going to have to rederive it. We're just going to use it. But let's read this together. A cake is removed from an oven at 300 degrees. And obviously, that would be implying that we're in Fahrenheit. And it's placed in a room that is 70 degrees. I hope it's pretty clear to you that T sub M would be 70. And furthermore, I could say when T equals 0, the temperature is 300. That type of stuff is very important because, remember, we're on the lookout to try to find some constants. And as we're trying to do that, we're going to very quickly make some adjustments. If I know that the room temperature is 70 degrees Fahrenheit, we're going to have this right here. Immediately, our Newton's law formula is taking more shape. We're getting more specific. But we're also saying after 3 minutes, the temperature of the cake is 200. So we're going to have another data point that we're going to be able to use. And the fact that you're given 2 data points is indicative that you've got a constant C sub 2. You also have that e to the k. To be able to find both, we need specific information about 2 temperatures at 2 different times. And that's why they're giving that to us. Once we use our data to get our specific particular equation, then we can answer how long will it take to cool to 100 degrees Fahrenheit from the time it was taken out of the oven. So let's use our first data point and see what it gives us. We're saying, look, I know that the temperature is 300 when the time is 0. Now, this is really e to the 0, and that's just a 1, isn't it? So at this point, we can subtract 70. 300 minus 70 is 230. And guys, right now, we could rewrite this formula with a little bit more specifics. We can say C2 is really the number 230. And right now, we're even more specific. Thank goodness our equation is really beginning to take shape. A big question that we have to address, could I take the 70 and the 230 and add them together to get 300? No, so tempting to do that. You'd break the order of operations, wouldn't you? You'd be adding before you would have done multiplication. So you're not allowed to do that. But what we are going to do now is we're going to say, you know what? There's this other data point that we could use. And I could plug in a temperature of 200 degrees. And I can say, you know what? That occurs 3 minutes after the cake was taken out of the oven. Now, at this point, you have 2 choices. You could solve for K, which you probably would have done in AMA or pre-calc. But, it's probably just as easy, even easier still, to solve for e to the k. I really like to do that. It's what calculus students generally do. So tell you what, I'm going to subtract a 70. 200 minus 70 is 130. And right here we could say this is e to the 3k, but I'm going to leave it just as k times 3. I hope you'd agree right now we could divide by 230. And we'd have e to the k times 3. By the way, we can just reduce that just a tiny bit. And how would I solve for e to the k? Remember, that's ultimately what we'd like to find. I want to get rid of that 3 up there. Raise both sides to the 1/3 power. Very good. Raise both sides to that 1/3 power. So I'd get e to the k would be this very peculiar looking 13 over 23 to the 1/3 power. And the reason why that's so helpful, guys, is because now I can come back here and say, you know what? That's what this thing is in our general equation. So I can go one step further and say, what is our equation? It's t equals 70 plus 230. But then we've got this 13 over 23, and it's raised to the 1/3 power, but then you multiply it by t, so it'd be t over 3. Okay? We doing okay? Right now you have something spectacular. You could find the temperature of the cake for any time. You could say, I wonder what the temperature is at 7 minutes or at 14 minutes, whatever you're dreaming up. You could find the temperature of the cake. But they're asking something a little bit different. They're saying, find the time when the cake cools to 100 degrees from the time it was taken out. How long will it take? Well, just finishing this up, you'll say, I know my ending temperature should be 100. And then I should just have to finish this up. So let's go ahead and see what we can do. I'm going to minus a 70. 100 minus 70 is a 30. Then I'm going to divide both sides by 230. And hopefully you can see some good things happening. You get 3 over 23 equals, here's your 13 over 23. T to the 1/3, or t over 3. How do we continue? I got to get my t. Yeah, take a natural log. Absolutely, definitely. You know, when we take an ln on both sides, you'll have ln of 3 over 23 right here. But thank goodness you'll get t over 3 to come down. And then just, continuing on, tell you what, I'm going to divide both sides by the ln of 13 over 23. I hope you can see why we're doing that. That's moving us toward getting t over 3. And now what? Well, ugly looking thing right there. You could just type in ln. You don't have to do pretty print. And while my calculator is not being cooperative, there we go. A little slow there. ln of 3 over 23. Then I'm going to say divide that by the ln of 13 over 23. And that whole left side is really 3.570. And I hope you can see our last step. Just multiply by 3. And since you still have that on the calculator, just say times by 3. And we're getting about 10.71 minutes. 10.710 minutes for the cake to cool. And that's our lesson.